Question 16. Gas X diffuses twice as fast as gas Y under the same conditions. If the relative molecular mass of X is 28, calculate the relative molecular mass of Y. A. 112, B. 120, C. 56, and option D. 14. So, interestingly enough, we covered diffusion, because keyword here is what diffusion, and and also molecular mass. So we covered this in question 1, where we said the word diffusion pretty much gave the way that it's a question under Graham's law of diffusion. So just a quick recap. Graham's law of diffusion states that the rate of diffusion of a gas is inversely proportional to the square root of its molecular weight, and if we were to have two gases, gas X and gas Y, the expression is given as this. And interestingly enough, that's what we have, gas X and gas Y. So a gas X diffuses twice as fast as gas Y. So let's say the rate of diffusion of gas Y, let's give it an arbitrary value of 1. So since X would diffuse twice as fast as Y, so X is pretty much 2 times Ry, so that's 2 times 1 equals 2. So we have the value of Y and X. If the relative molecular mass of gas X, that's Mx, is 28, what would be My? That's pretty much what we're looking for. So first things first, we can just square both sides to remove the square root sign. So we pretty much have Rx Ry squared equals My divided by Mx. That's pretty much Rx happens to be 2. So 2 squared divided by 1 squared equals My, that's what we're looking for. And Mx is 28. So multiply both sides, My times 1 equals 4 times 28, and My would give us 112. That's 112. So comparing the options, option A matches with what we got, so that's our answer. Again, the reason why we assume the value for Ry is because of this term is twice as fast. So in the end, it's more of ratio. No matter the value you use for Ry, so long as you say Rx will be twice Ry, you're still going to get the same thing. You think that's a lie? Let's check. So Ry, let's assume Ry to be 4. So Rx, since Rx is twice as fast, it's going to be what? 2 times 4, and that will be 8. So Rx over Ry would have been 8 divided by 4, and that would have been 2 divided by 1, and that was what we had here. So no matter the value so long as you stick with the condition given, you should be fine. So moving on, we move on to question 17. Oh, cigarette. The filter in a cigarette reduces the nicotine content by A, burning, B, adsorption, C, evaporation, D, absorption. So I think let's try to have I think this is how it goes. Yeah. So this is usually in brown color, and this is white. So this is actually where the filter in the cigarette, this is where it is, the inside part of the brown label of the cigarette, that's where it is. So the way it supposedly works is the moment you set up the cigarette and you're already smoking it off, as the smoke is moving through to the mouth of whoever is smoking it and all, the filter is supposed to diminish the nicotine content. At least that's the basic idea of how it's supposed to work, or how it's working. So let's use that to answer our question. So how does it reduce it? Does it reduce it by burning? Obviously no, because it doesn't like burn. That's not where the burning is occurring. Adsorption, let's put a pin on that. Evaporation, definitely no evaporation. Evaporation has to do with more or less boiling and or similar to boiling, and that's not what's happening here because there are no liquids here. So absorption, absorption more or less deals with liquid also. Imagine spilling water on the floor with paper. The paper pretty much absorbs the water, and over here there are no liquids, so it can't be absorption. So with just by mere elimination, we can say that it's not burning, it's not evaporation, it's not absorption. So we are definitely left with adsorption, and that's actually the correct option. Again, don't confuse it with absorption. Absorption deals with water. However, adsorption can be with different forms of matter. Question 18. Which of the following has an isomer? A. C6H6, B. C2H6, C. C4H10, and finally D. C2H4. So what exactly is an isomer? So isomers are pretty much compounds that have the same molecular formula but different structural formula. So that's the key details. Same molecular formula, different structural formula. It means if you are able to have two compounds that have the same molecular formula. So quick recap, what exactly is molecular formula? Pretty much any formula that shows you the exact number of atoms present in a compound, that's a molecular formula. Example now is H2. H2 tells you you have 2 hydrogen and 1 oxygen. So that's molecular formula. So an isomer pretty much says two compounds can have the same molecular formula. So that's where structural formula comes into play, because only one compound can only have one structural formula, no more no less. So let's look at the options we have here. So C6H6, that's benzene. C6H, that's option A. Benzene. Okay, let's use carbon representation. Yeah. And obviously, okay, hydrogen. There's C, hydrogen. Now, can this be represented in any other way? No, benzene cannot be. There is no tweaking. There's no way we can adjust the atoms and would have a valid structure. So that means benzene is definitely not an isomer. Next option, B, we have C2H6. That's C2H6. 1, 2, 3. This is ethane. Same thing with benzene. There's no way we can rearrange this to form another compound, another valid structure, because emphasis on the word valid. So since there is no way we can form a valid structure with this, this is also not an isomer. Next one is butane. We have H, 10 hydrogens. This is option C. So 10 hydrogens. Unlike the previous ones that we've not been able to modify the structure, here we can decide, rather than having this carbon at last, we can bring it to probably the second carbon and all. So we can have something like this basically. C. So we can have still the same 4 carbon atoms and 10 hydrogen atoms. What just happened here now is we've been able to let's say tweak the structure. We pretty much moved this ending carbon to the second carbon, and we still happen to have a valid structure. How do we know it's valid? Well, first and foremost, all the carbons still maintains their 4 bonds and also we stick to what the molecular formula of what C4H10. If you were to count the number of carbon here and hydrogen, you would see it's C4H10, and also same thing here. The last option, option D, that's C2H4, that's C. The remaining two bonds, so we have a double bond here, and also at most we can only just swap around the hydrogen, and that's not really causing a change in the structural formula. So among all these options, option C seems to satisfy. We're able to play around with option C, so that makes C our answer. So moving on, question 19. Question 19 says when temporary hard water is boiled for some time in a kettle, the inner surface of the kettle is coated with a deposit of A, calcium tetraoxosulphate 6, B, calcium trioxocarbonate 4, C, calcium hydrogentrioxocarbonate 4, and D, aluminium trioxocarbonate 4. So what exactly is temporary hard water? So generally, temporary hard water contains calcium or magnesium ions in the form of calcium hydrogen trioxocarbonate 4 and or magnesium hydrogen trioxocarbonate 4. So what we pretty much have is CaHCO3. So yeah. So whenever this is boiled, it decomposes. We have the product that form CH CO3, H2O, and CO2. We don't really need to bother ourselves balancing. Oh wait, I think it's balanced. Yeah, the equation is even balanced already. So this is solid, this is liquid, and this is gaseous. So we're talking about the deposit. So obviously it's going to be a solid. So this is the deposit in question. So what exactly is CaCO3? So naming it, we have calcium carbonate, or more accurately, we have calcium trioxocarbonate 4. So it's not aluminium, it's not this, rather it's this. So option B is the correct answer.